Before electronic computers, people built mechanical computers to perform specific mathematical operations. One such machine was this, Albert Michelson's harmonic analyzer. This 19th century machine adds together cosines to create intricate patterns. Amazingly, it also does the inverse operation. It can take a pattern and reveal the cosines that, when added together, will approximate it. This operation is called Fourier analysis and is possibly the most important mathematical technique of the past 100 years. Without Fourier analysis, there would be no MP3s, JPEGs, or cell phones as we know them today. To celebrate this stunning machine and to gain a greater insight into what Fourier analysis is and how it works, I'll share in this video some history of this analyzer and then in 3 additional videos detail its operation. In synthesis, I go step by step and examine the key components of the machine and how each plays its part in adding cosines. In analysis, I show you how the machine uses the same mechanical motions to find the frequency components of a signal you want to analyze. And in operation, I show the steps an operator of this machine must go through to perform these calculations. This machine's designer, Albert Michelson, was famous for measuring the speed of light, yet he also measured many other properties of the universe precisely, like the diameter of stars or the rigidity of the Earth. In the late 19th century, he performed Fourier analysis by hand to help resolve fine details of the light emitted by vaporized elements. He was doing an early version of Fourier transform spectroscopy. These hand calculations were laborious, so he invented this machine to automate these calculations. He built a prototype machine similar to this one in 1897, and then a larger prototype 4 times the size a year later. The machine was then commercialized by William Gartner and Company. They made precision scientific instruments often designed by Michelson. In their 1904 catalog, they advertised this machine, which can add up to 20 different sinusoids, as well as a larger version that calculated with 80 sinusoids. We know that in the early 20th century, Gartner sold at least 4 of these machines, and based on that, it seems this 20-element machine sold for around $225, and that it was likely made between 1901 and 1910. After this period, the machines are mentioned only occasionally. We found pictures of several different configurations until it made one last public appearance in an improved form at the 1933 World's Fair in the Great Hall of Science in an exhibit called The Magic of Analysis. Our machine has an unknown history. We're not sure when it arrived here on the University of Illinois campus. We only know that for at least the last 40 years, it is set in a glass case in Altgeld Hall, its gears completely still. Join me as I bring back to life this stunning mechanical computer. I'm Bill Hammack, the Engineer Guy. This astonishing machine uses just gears and springs to add together sinusoids. This synthesis, as it's called, creates beautiful patterns that look nothing like sinusoids. The machine produces patterns like beats, smooth peaks, sharp corners, or even jagged edges. And these can all be made using this function. Here's how this mechanical marvel implements that function. The machine has 5 key sections. First, a crank that varies x. Second, gears and cams that generate frequencies. Third, just a little bit above that, rocker arms that create the sinusoids, and amplitude bars to weigh those sinusoids. Fourth, at the top, springs and levers that add together these weighted sinusoids. And lastly, on the front side, a mechanism for recording the sum on a piece of paper. At the heart of the machine lies 2 sets of gears. This cone-shaped set has 20 gears that vary linearly in both size and number of teeth. It engages the cylindrical set of 20 gears, all of the same size. Watch what happens as I turn the crank. The gears on the cone-shaped set all rotate together. The gears on the cylindrical set can rotate independently, each at a rate determined by the corresponding gear on the cone. This gear rotates twice as fast as this gear, this one 3 times as fast, and so on. These gears generate the different frequencies. A cam on each gear drives the rocker arm up and down via a connecting rod. As each gear rotates, the corresponding rocker arm traces out in up and down or a sinusoidal motion with the same frequency. For example, the first rocker arm oscillates to produce cosine 1x, the 10th produces cosine 10x, and the 20th cosine 20x. Of course, the arms in between produce cosine 2x, 3x, 4x, and so on. At the bottom, a series of long vertical bars rest on each rocker arm. At the top, these bars attach to levers that are spring-loaded. The position of the rocker arms on the bar determines the coefficient. As I slide this bar to the edge of the rocker arm, the lever at top rises. That's a coefficient of plus 10. When I return it to the rocker arm's pivot, the lever returns to its original position, a coefficient of 0. And as I continue to slide to the opposite edge, the lever drops, a coefficient of minus 10. Now, let me show you how the machine sums these sinusoidal motions weighted by their coefficients. I'll set the machine up to produce beats using sine 12x and sine 10x. Each lever at the top of the machine has a spring that connects it to a pivoted bar. A large spring balances the pole of the series of springs on the levers. If we look at the top, we see the spring extends more than a foot above the machine. As I turn the crank, the amplitude bars drive the spring-loaded levers up and down. This in turn moves the pivoted bar. Because the springs all pull on the same pivoted bar, their displacements are summed. If we take a close look at the pivoted bar, we see that it sweeps out a small arc. We can barely see it go up and down. Let's return to the front to see how the machine amplifies this motion and then records it. This lever magnifies the result from the summer, but it's still a very small motion. A wire connects the magnifying lever to a set of concentric wheels that amplify further the motion. This wire pulls on the hub of this inner wheel, while a different wire is wrapped around the outer wheel. The wire attached to the larger wheel moves the pen vertically as a set of gears connected to the crank has been moving the paper horizontally under the pen. This is the same crank that rotates the gears to create the sinusoids and that also moves the pen up and down. Amazing as that synthesis is, that adding together of sinusoids, the machine does something even more fantastic to me. Given any periodic function, it will calculate the correct mix of sines or cosines needed to synthesize that function. Understanding that process, called analysis, will, in the next video, enrich our understanding of the machine by looking at its operation from a different point of view. I'm Bill Hammack, the Engineer Guy. In the previous video, I showed how turning the crank on this machine generates 20 different frequencies, also known as harmonics, which are turned into cosines here, multiplied by coefficients, then summed, magnified, and the resulting function plotted here on the front. This process is called synthesis. But this machine is called a harmonic analyzer, which means it can be used to solve the much more difficult inverse problem called analysis. For example, if I want to plot a particular function here, how do I set the amplitude bars to produce it? To illustrate how this machine does analysis, let's start with a square wave. First, we use some unique properties of the square wave. Since it's periodic and even, all of the information that function carries is contained in half a period. So we'll take that half a period and sample it at 20 equally spaced points. We use the values of these points as the inputs for the machine. When we turn the crank, we produce a new function that reveals the correct coefficients. To see how we get these coefficients, we'll look at the side of the machine. As I turn the crank, the tips of the rocker arms form a sinusoid. The indices on the rocker arms run from high on the left to low on the right. I'll flip the video to make it a little more intuitive. When the rocker arm tips are lined up in a straight line, we'll call that crank number 0. If the horizontal axis runs from 0 to pi, and the vertical axis from -1 to +1, then we can describe the position of the rocker arms with a cosine. Every 2 turns of the crank increases the frequency of the cosine by 1. At these even-numbered cranks, the values of the function on the platen yield the coefficients we're looking for. Let's rewind and watch the plot and the rocker arms simultaneously. If we pause briefly at every second crank, a point is marked on the function. We create a total of 20 points. If we look at the output from the machine and compare it to a sync calculated by a computer, we see that they are very similar. Now, we'll take the data points from the sync, scale them, and use these values on the rocker arms. Remember that our goal is to program the analyzer so that it will plot a square wave. Now, as I turn the crank, the pen writes a horizontal line, then drops and writes another flat section, which amazes me because we're adding only cosines. And then it rises to write another horizontal line. Of course, what we're seeing is a square wave. What I've just shown with the machine is an essential feature of Fourier methods. I can take a function, perform harmonic analysis, extract the coefficients, and then synthesize that function to approximate the original. So, now that we see that this machine can do harmonic synthesis and analysis, I'll show you in the next video some details about how to set up the analyzer to perform these calculations. I'm Bill Hammack, the Engineer Guy. In this video, we concentrate on the machine itself, how to set up, adjust, and calibrate the machine for use. Let's look at the 5 main things we can set when using the analyzer. The amplitudes of the sinusoids we're summing, the horizontal scaling, the vertical scaling, choosing sines or cosines, and lastly, adjusting the pen so it writes correctly. Let's start with setting the 20 amplitude bars. As we saw in earlier videos, this lever's position on the rocker arms determines the value of the coefficient. We set that position precisely using this tool. It's a small brass bar with an adjustable stop. The brass bar has markings that go from 0 to 10 in increments of 1/10. The stop slides along the bar and can be fixed at precise points. Here we slide the stop up to 5, place the tool on the rocker arms, and push the amplitude bar into place. When I slide the stop all the way up to a large number, like 10, I slide the amplitude bar out to reach the end of the tool. Recall this measuring stick goes from 0 to 10. So how do we set negative amplitudes? We set the measuring stick to the magnitude we want and use it on the opposite end of the rocker arms. On the left are the positive coefficients, and on the right side are negative coefficients. The amount of horizontal scaling depends on how fast this platen moves as the crank is turned. The platen can move slowly, at a medium pace, or very fast. This gear train that moves the platen consists of these 6 gears. The first gear is on the shaft of the crank. A chain connects this first gear to the second gear, which you can see up close here. On the same shaft is the second gear, and sitting just behind it is a third gear. It has 12 teeth and engages the fourth gear. This fourth gear has 120 teeth. Behind and attached to the fourth gear is the fifth gear. This gear has 12 teeth and engages the rack, which is the sixth gear. You can see from the back how the rack runs the full length of the platen. I can adjust the horizontal scaling by changing the first and second gears. First, remove this tapered pin and pull off the crank handle. Next, unscrew the nut that holds the other gear in place, and then unlatch this gear system so it disengages from the rack. Here's the same motion, but from a different angle. Notice how the chain is now slack and so can be removed. The machine came with 4 gears, 1 small, 2 medium, and 1 large. I'll remove a medium gear from the crankshaft and replace it with a small gear. And then replace the medium gear above it with the large gear. Then affix that gear with the nut, replace the chain, attach the handle, secure it with a pin, and then relatch the gears. Now, let's look at 3 gear combinations, large and small, medium and medium, and small and large, and see how each translates the platen. I'll start with the large, small gear configuration. When it reaches halfway, I'll start the medium gear set. Notice the pins move up and down in sync. When the first gear set is 3/4 of the way, I'll start the third gear set. They finish all at the same time. This large-small gear set yields twice as many periods as the medium gear set. And the small-large yields half as many. In contrast to the horizontal scaling, the analyzer uses a different method to scale up and down. At the top of the analyzer, the vertical scaling is determined by the magnifying lever. This cylindrical rod extends from the pivoted summing bar. The position of this knob on the lever determines the vertical scaling of the output. When the knob is toward the end, the amplitude is at a maximum. When the knob is about halfway, the amplitude is reduced. And when I place it all the way inward, the amplitude is at a minimum. A second rod perpendicular to the first controls the vertical offset of the output. This knob slides up and down, and the wire wrapped around the end connects the rod to the inner hub of the magnifying wheel, which in turn is connected to the pen. Let's look at the pen and the knob simultaneously. We'll mark the current position and move the knob up. Notice a small movement of the knob yields a large movement of the pen because a set of concentric wheels connect the wire attached to the knob and the wire attached to the pen. The diameter of the outer wheel is 5 times that of the inner wheel, and so the pen moves vertically with 5 times the magnitude of the knob's motion. We can set the analyzer to use either sines or cosines. We do that by configuring these gears: the cone gear set, the cylinder gear set, and the pinion gear. Recall that when we use the machine, the gears on the cone set engage the gears on the cylinder. To change between sines and cosines, we need to disengage the 2 sets of gears. Unscrewing this knob allows the cone gear set to swing away from the cylinder. You can see it more easily from the top. This action completely disengages the cone and cylinder gears. Notice that each gear has a notch and can be rotated independently. The goal is to put the sinusoids associated with each gear in phase. You can see that sinusoid's motion from the side. As I rotate the gear, the rocker arm above moves in sync. Internal cams drive the connecting rods up and down. When the notches are aligned, the cams and the connecting rod are also aligned. Aligning the notches is a bit tedious, but it only takes a few minutes. Once they're aligned, I can position the gears for sines or cosines by engaging the cylinder gear with this pinion. This lever pushes the pinion into contact with the cylinder gear set. Notice the notch. When all the notches are in this position, the machine is set for sines. If I rotate the gears 90 degrees, this sets the gears for cosines. Again, if the notches are on the side, the machine calculates sines, and if they're on top, the machine calculates cosines. Why is this? When the notches are at the top, the rocker arms are at their maximum travel. That's like a sinusoid starting at its peak, which is equivalent to a cosine. When at the bottom, the rocker arms are at their lowest point of travel, which is like a sinusoid starting at its trough. This is like a negative cosine. And when the notches are on the side, this is a middle position, which is equivalent to a sine. If we set the amplitude bars for a square wave and set the machine for cosines, we get this even function. It's even because it is mirrored around the y-axis. And then keeping the amplitude bars the same, but setting the gears for sines, we get this odd function. It's odd because it's rotated 180 degrees about the origin. The output of the machine is recorded by a pen mechanism. This brass pen holder, which looks authentic, was made in our shop because the original is long lost. A long square brass rod rests gently in an open bracket, its top attached by a wire to the outer rim of the magnifying wheel. I attach the pen to this brass block. A square rod with a cylindrical end fits into the block and a set screw secures it. A removable rectangular frame secures the pen to the brass block. Here I attach the frame, insert the mini Sharpie pen, and secure it. I orient the pen about 45 degrees against the direction of travel of the platen, and then press it up lightly against the paper. As I turn the crank, the pen smoothly writes the function. Oddly, if the pen is perpendicular to the direction of travel, the plot tends to have flat peaks and troughs. And if the pen is oriented with the direction of travel, it's even worse. This particular machine, with gears to produce 20 frequencies, was likely built around 1915 and is a descendant of the first analyzer that Albert Michelson ever built. He used what he learned from that first model to construct an 80-gear machine and even planned to build a model with 1,000 gears. What a wonder that machine would have been. I'm Bill Hammack, the engineer guy. I'm Bill Hammack, and this is a page-by-page commentary of the entire book, Albert Michelson's Harmonic Analyzer. I'll share with you information that didn't make it anywhere else. I assume that you've watched the video series and so have a sense about how the machine operates. So now we see the machine and a picture of me. Notice the labels. We try to make them appear as if they were printed on the thing they're labeling. Look for them throughout the book. The introduction focuses on Albert Michelson. Likely you've heard of him from the Michelson-Morley experiment or his measurement of the speed of light. At the time he designed this analyzer, he was a professor of physics at the University of Chicago. Now, on the right here, you see the machine marked with dimensions. Well, this machine was most certainly built using inches as units, as was the standard at the time. We decided to label dimensions in metric units. This visual table of contents shows you the main parts of the machine, and it lists the pages where that part is located in the book. These pages also serve as a visual table of contents. We link the parts of the analyzer to their mathematical function. Here we do that for synthesis. On the left, we go through term by term the synthesis equation and how to think about each term individually. There's a more detailed mathematics section of the book on page 98. On these pages, we do the same visual table of contents, but for analysis. Now, it's easy to understand what analysis does. That's shown visually on the left page. It takes a signal and tells you what sinusoids to add together to approximate that signal. But it's hard to understand exactly how it does this. This difficulty is exactly why this machine was built. This section is the meat of the book. We take you part by part through the machine. Turning the crank on this machine is really cool. It takes a full 80 cranks for the entire machine to make a complete cycle. When you crank a whole cycle, you can literally feel when the gears are in phase. When a rocker arm is pushing an amplitude bar upward, the crank requires more force, and when all the gears are in phase, the crank is much harder to turn. If you look carefully here, you see a small fiducial mark. It helps to orient the crank when reattaching it with a tapered pin. There are 4 different combinations of attaching the crank and the pin, and only one will fit properly. The cone gear set is probably the most distinctive part of the entire machine. It's not a single gear shaped like a cone, but rather it's a set of gears that form a cone. We've never seen this arrangement of gears in any other type of machinery. When we first got the machine, we expected the gears to make clicking or clunking sounds. Turns out it's very smooth and incredibly quiet. The crank does not rotate the cone gear set directly. This gear is attached to the crankshaft and in turn engages the cone gear set. This is why it takes 4 turns of the crank to rotate the cone gear set by 1 revolution. Without this gear reduction, the crank would be more difficult to turn. Here you can really see the grime on the cone gear in many of these photos. Notice the shape of the teeth on the smallest gear on the cone. They're much pointier than the teeth on the other gears. The cylinder gear set is driven by the cone gear set, but unlike the cone gear set, when operating, you have to often touch these gears because you adjust them by hand to set the machine for sines or cosines. We often get the question, do you have to set them all to be sines or cosines? And in principle, no. You could independently set a gear to be a sine or a cosine or even a phase-shifted sinusoid. In practice, though, it'd be hard to do because when you turn a gear, it tends to turn the one next to it. The cam we show here is a bit schematic. Without taking apart the analyzer, we could not determine exactly what it looked like. One reader wrote me that he thought it was more likely an eccentric hub. Each rocker arm has 2 holes on its left and right sides, about an inch away from the pivot. We're not sure what they're there for. At first, we thought that a rod could be inserted through the holes in order to align the rocker arms. This is nearly impossible without binding the rod and rocker arms. Plus, aligning the arms is more easily done by aligning the notches on the cylinder gear set. So the purpose of these holes remains a mystery to us. While watching the synthesis video, you may have noticed that these trails coming off the tips of the rocker arms are not perfectly sinusoidal. This distortion is primarily due to the fact that the tips are not moving perfectly vertically. They're moving in an arc and therefore also have some horizontal movement, making the waves look a little sharper. Notice that you can also see sine waves on the tips of the rocker arms. The fact that the motions of the machine produce sine waves in 2 different directions hints at a deep concept in Fourier analysis, the concept of duality. This is an extremely important concept in modern mathematics. For this machine, it means you can transform back and forth between the function as represented on the rocker arms or as represented on the output at the front of the machine. And they're both equally valid ways to describe that particular function. One reader asked what holds the amplitude bars in place. It's just friction. The springs at the top of the machine press them lightly against the rocker arms. In fact, you can sweep the amplitude bars out past the ends of the rocker arms. It's alarming when it happens. The amplitude bars crash into the base of the machine. The first time I did this, I thought I'd broken the analyzer. But the machine is resilient. Just put the bar back on the rocker arm, and it's fine. Notice that the amplitude bars are more rusted at the base than at the top. You generally touch the bottom to move the bars, so we guess that moisture from hands accelerated the corrosion. The measuring stick is not precisely a part of the machine, but it's an accessory tool that came with it. We believe it to be original because the style of the knob matches knobs on the magnifying lever. Also, it looks very similar to tools shown in pictures of other analyzers. The measuring stick is a very simple tool, but it works well. It is accurate and it's fairly repeatable to use. The springs and levers at the top are integral to the machine's operation because they are where the summation occurs. These springs were Michelson's great insight. He'd considered using fluid pressure and electrical currents to add sinusoids, and decided that springs were, and I quote him here, the simplest in practice. Despite their importance, it's easy to forget about these parts because they are a foot or 2 above the head of the operator. The springs in this machine are in great shape, but they can wear out. I came across a report by a graduate student at the University of Chicago who, in the late 1920s, used one of Michelson's analyzers, likely one built 20 years or more earlier. He reports that, quote, by the time I got my hands on the machine, the springs had different force constants so that you got some startling results. Here's the underside of the summing lever. In the video, we call this a pivoted bar, and then realized when writing this companion book that a pivoted bar is, of course, a lever. We use the word pivot because the most surprising aspect of this lever is the large knife-edge pivot that it uses. This was some kind of very careful design choice. Likely it was to reduce friction. Now, keep in mind all of the terms we use, like amplitude bars, rocker arms, and so on, were invented by us. There was no user's manual or workshop plans for this machine. This counterspring counterbalances the pull of the 20 smaller springs. The curved, tapered post that holds up the spring can be moved up and down to adjust the tension. The summing lever has a limited range of travel and needs to be kept around its middle point. If the pull of the counterspring is too much, that is, the post is too high, then the summing bar will tip too far downward and get stuck. And if the post is too low, the summing lever will drop and will not be held up on its pivot. Once the height of the counterspring was set, we did not need to adjust it further. This magnifying lever amplifies the motion from the summing lever. It's a simple brass rod with a threaded end. It can be unscrewed from the angled bracket that attaches it to the summing lever. When we brought the machine to our shop, it didn't have a writing mechanism, and so I took data by hand. I would measure with a ruler the motions of the tip of this arm and then plot its position against the number of cranks. I recall getting tired of measuring the small motion, and so I had the machine shop make a 3-foot-long magnifying lever so it would sweep out a much larger, more easily measurable arc. And this long arm weighed too much and never worked. This vertical rod allows the operator to adjust the vertical position of the output on the paper. In electrical engineering, you would call this the DC offset. Adjusting this knob is very difficult because the position of the pen is very sensitive to small changes on the rod. Also, the magnifying lever which it's attached to can wobble up and down during adjustment. The magnifying wheel further amplifies the motion of the summing lever. We noticed that the metal in this wheel was not magnetic, and so we thought it might be aluminum. We learned later from a catalog by the analyzer's manufacturer that they often used an alloy of aluminum called magnalium. They describe it as very strong, white, and light non-corrosive alloy, and so that's likely what this wheel is made from. The idea was to get a very lightweight wheel. You can see here how we wrap a wire around the hub of this inner wheel. Note there is no lip, and so sometimes during adjustments, the wire would slip off and unravel. This malfunction was particularly frustrating because the wire attached to the magnifying lever and the wire attached to the pin would get tangled. The platen has 2 brass clips that hold a piece of paper. We found we got the best results when we used glossy photo paper. Anything else seemed to have too much friction. The platen itself is surprisingly heavy. The translational gearing controls the horizontal scaling of the output. I find it fascinating that the scale is adjusted by changing the speed of the platen relative to the crank's motion. The next 6 pages detail the translational gearing. It is very compact, and so it takes quite a few photos to really document here. You'll likely find the labels on the images useful to keep you oriented. On this page, we're just showing you how the gears are exchanged. Notice that on the left, the threaded nut has been removed, and on the right, the crank has been removed. Careful study of these images will likely repay the time spent with them. The left is a view from the top, and the right is a view from the back. The pen mechanism proved to be the most challenging aspect of the machine, mostly because when we discovered the machine, the writing mechanism was missing. To recreate it, we looked at photos, but these didn't help too much. First, we found several different types of writing mechanisms, none of which seemed to fit our machine. Or second, the photos often didn't have enough resolution to really see what was going on. So this is our best guess. The piece you're looking at was made by our machine shop. The holes in the brass block were drilled to reduce weight, but we're not sure now if we really need to do that. Notice that the ink pen is a Sharpie spray painted to look metallic. We don't know what kind of pen they would have used. I suspect it was a fountain pen of some sort that just barely touched the paper. We thought about that, but concluded it would be too messy. We also tried a pencil, but found it had too much friction on the paper. The pinion gear is not actively used while the machine is in operation, yet it is essential for setting up the machine. It is used to set the machine for sines or cosines. This lever is attached to cams that push the pinion gear into contact with the cylinder gear set. This brass spring pushes against the pinion and keeps it from contacting the cylinder gear set when the lever is disengaged. Notice this little post here. We've called it the mystery post because we're not entirely sure what it does. It seems like it may serve as a stop to prevent this lever from being pushed down too far. Interestingly, it has the same diameter as the vertical rod extending from the magnifying lever. On the base plate, there's a ring of wear that matches the knob from that vertical rod. Perhaps it was used to store an extra knob. We really don't know. Provenance is a term used for a historical object. It's the documented story of who owned it and where it was kept, so the object can be traced through time. We don't have anything like that for this machine. I've visited the university archives and looked for any hint of the machine and turned up nothing. The nameplate clearly tells us who built it, William Gartner and Company. The Gartner Company still exists today as Gartner Scientific Corporation. They make ellipsometers, microscopes, and other optical instruments. A larger version of this machine was also built. It calculates with 80 sinusoids instead of 20. We found two distinct models of the 80-gear machine. Note the difference in the cone gear of each. In this model, the cone gear is very much like the cone set on our analyzer, but 4 times the size. It truly is humongous. In this, we assume later model, the cone gear is different. It appears to be made of 2 separate cone gears, each driven at a different rate, thus allowing for more compact gearing while still generating the same motion as a single giant cone gear set. On the right-hand page, you see a photo of this analyzer in its glass case. If you want to see it in person, just visit the University of Illinois and go to Altgeld Hall. You can find this machine on the 2nd floor, not too far from the mathematics library. The next 16 pages show output from the machine. For each output, we use an input schematic to indicate how the amplitude bars were set. These are cosines, each of a single frequency ranging from cosine of 1x to cosine of 20x. If you look closely, you'll notice that all the amplitudes of each cosine are not exact. This could be caused by the springs wearing out and having different spring constants, but a much more likely cause is different friction between the pen and the paper. If the pen is pushed too far onto the paper, there will be increased friction that resists the movement from the summing lever. This will result in a smaller apparent amplitude. Note the squash section in cosine 19x. What happened here was the paper was not flat on the platen, but bulged out slightly. When the pen reached the bulge, there was a sharp increase in friction, and the pen could not move up and down as freely. In the next 2 spreads, we move a square wave across the rocker arms. It produces some very cool-looking patterns. On this spread and the one following, we've sampled a cosine of varying frequencies. We use cosines of 2, 1, 1/2, and 1/4 periods. Notice as the period decreases, the peaks in the output move closer together. On the left, we've input a square wave to produce a sync to produce a square wave, and some frequencies to produce beats. On the right-hand page, the top 3 inputs are Bessel functions of various parameters. Keep in mind that we didn't use the same translational gearing for each calculation. You can determine what gearing we used by just counting the periods. For example, the plot on the top of the left-hand page was made with the medium and medium gear combination, shown on page 57, because it has 1 period, while the graph below it, the square wave, was made with the large-small combo because it has 2 periods. On the left are examples of some arbitrary input and output pairs. The output on the right was produced with the machine set for sines. Everything else in this output section was done with the machine set up to calculate with cosines. This is the key paper about the analyzer. It was written by Michelson and Samuel Stratton. Often the machine is called a Michelson-Stratton analyzer, but we don't use this term because Michelson clearly had the idea before he worked with Stratton and had even built a 20-wheel version of the machine as a prototype. Stratton, though, was no doubt important in getting the larger version built. Stratton was head of electrical engineering at the University of Illinois before moving to Chicago to work with Michelson. Stratton had a long association with William Gartner, whose company built this analyzer. We suspect, but could never prove it, that Stratton was seminal in getting the analyzer described in this book to the University of Illinois. This is a schematic of the key components of the analyzer. This paper contains a lot of data produced by this 80 sinusoid machine. Because it had more sinusoids, the output it produced is sharper and more detailed than the output from our 20-gear machine. The graphs on the left-hand side show you how to analyze a function that is neither even nor odd. In this book, we mostly considered even functions that require only cosines to be approximated. We could just as easily have used only odd functions and then used sines throughout. In these 2 pages, we go deeper into the mathematics. Our goal is to lay out the math in a way it would be discussed in a class on Fourier analysis so that someone who has had such a class can link up what they learned to the analyzer. Another thing to note here is that the derivations of the equations show, especially for analysis, the simplifications and approximations made by the machine when calculating. These spreads show the analyzer at 8 different angles. It's a great way to imagine walking all the way around the machine. It feels like the closest we could get to letting you be there in person. We've worked with this machine for 2 years. We spent the first months getting it to write properly. It took countless hours of each of us poring over the machine to discover all the parts and understand how they work together. We had many debates about the best way to show the machine's operation for both synthesis and analysis. Eventually, we realized the videos weren't enough to capture all of the magnificent mechanics, so we set upon photographing and assembling the book. It's hard to believe it's been 2 years since we first discovered the machine. We will certainly miss working with the analyzer, but we hope with the videos and the book that you can enjoy it as much as we have. Thanks for going through the book with me. I'm Bill Hammack, the Engineer Guy.